All right, guys. So we're going to finish up substitution method by talking about the exponentials. Now, exponentials, they really don't come into play a lot until you get closer to a Calc 4 type situation. And then exponentials seem to just pop up all over the place. So I want to kind of go over them. They're important, but they're at the end for a reason. Parentheses are most important. Fractions are second most important, and then the exponentials are the third most important. Okay? Now that's not to say that the specific area of science that you go into doesn't prioritize one of those over the others. And so for your particular situation, this may be the most important one. So they're all important, just trying to go off of generalities. So in this situation, we're going to be dealing with e, although it doesn't have to be an e, raised to some power. Now, if you remember from the notes that we talked about last week, we had a rule for dealing with e. Now that 9 can just be moved out front. So that's 9 times the integral of e to the 6x dx. Okay? And then that's just going to be 9 times 1 over 6 e to the 6x plus c. That number in front of the x comes down. Okay, and so this is going to give us 3/2 e to the 6x plus c. Okay, that's the answer. The formula that we use to make that happen, the formula is the integral of e to the ax dx is equal to 1 over a e to the ax. Okay, so right here is the formula. Now there's a couple of things to notice about this formula that make it very, very limited. Let me just write formula. The first, that x in the formula is not to the second power, or third, or fourth, or fifth, or whatever. So if you have e to a number times x, and that x has an exponent, you cannot use this formula. You have to do substitution method. Okay? The second thing, there's nothing else up here. That is a 6x. If I throw in, like I did over here, another number, 6x plus 7, now it no longer fits the formula. The formula is e to the ax, not e to the ax plus something else. So in this situation, we will have to let u be equal to the entire exponent, okay? And then it will go away. So let's go ahead and do a couple of these. So what we're going to do is the entire exponent is going to go away, and so u is equal to 6x plus 7. Okay. And then du is going to be equal to 6 dx. Then all I have to do is move that over, and I have 1 over 6 du dx. Boom, and I'm ready to go. So this is going to give me the integral of 9 times e to the u times 1 over 6 du. The 9 and the 6 can be moved out front. Just like so. And I'm ready to go. Now, just to kind of remind you guys about what we talked about, if you have the integral of e to just a letter, no exponents, no craziness, that is an exact copy of itself. So this is going to give me 3/2 e to the u plus c. And then I can plug back in what my u was, 6x plus 7. So this is 3/2 e to the 6x plus 7 plus c. Now, I haven't mentioned it in a while, but I am very careful to include a plus c on all of my answers. This is very important. They do not go away. If you do not have a start or a stop, you have to have a plus c. This will be true in Calculus 3. This will be true in differential equations. You have to have a plus c. And in Calculus 3, and even in Calculus 2, you will have multiple plus c's. Okay? So that stuff's never going to go away. So right here, just like we did on the previous one, the entire exponent is going to be the u. So that's going to be u equals 5x squared. And so du is equal to 10x dx. Move that over. And that is going to be 1 over 10x du is equal to dx. And so now that I've got all of my pieces put together, I can go up here and plug everything in. So that's going to be 8x times e to the u times 1 over 10x du. Now I can move everything out front. And I'm right back to what I had on the previous problem. The stuff out front will reduce, so that's going to be 4/5 or 4/5 e to the u plus c. And so that is going to be 4/5 e to the 5x squared plus c. Now, while everyone gets caught up to here, I do want to kind of point out something we mentioned in the last video, that in a science problem, this is just the first antiderivative. You may have to take a second antiderivative, and substitution method may not work on the next one. If you looked at this right here, and this was your starting point, the 4/5 e to the 5x plus e to the 5x squared plus c, if you have to take the antiderivative of that, substitution method would not work. You would have to use a different method. And so, and it may not be possible. You end up with sometimes where it's not, and you have to resort to something called numerical integration. We'll talk about numerical integration later in the next unit. We'll do a whole lesson on it. And numerical integration has really only hit a practical usability since the advent of modern computers. And you'll see why doing numerical integration by hand back in the day would not have been a practical option. It is a last resort option. Even when I was a college student 20-some years ago, it was not. It was just starting to become an option due to computers. You know, they really were just now starting to get to a point where their processing power could actually reliably do numerical integration. All right, so let's look at this one right here. So once again, I'm going to let the entire top of the exponent, that entire exponent, be my u. And so that's going to be sine of 3x. Now, I didn't choose this one because I thought you would have a lot of trig functions as exponents. I'm not saying it doesn't happen, but it's pretty rare. I chose this one mainly so that I could go back over how to take the derivative of a trig function again. So the derivative of sine is cosine. Boom. So that comes straight down. And then you have to multiply by the derivative of the inside. Okay? And that is chain rule. Just to remind you guys of chain rule. And so du is equal to 3 cosine 3x dx. That should all probably be the same step. And then I can move everything over. And that's going to be 1 over 3 cosine 3x du equals dx. And so now I've got everything set up. Those cosines are going to cancel out. And I'm going to have a fairly nice day at the races. Okay? And so that's going to be the integral of cosine 3x times e to the u. So that's good. That whole issue is gone. And that's going to be 1 over cosine, well, 3 cosine 3x du. Again, if these trig functions did not match up, I would be in trouble. I would be in trouble like no other business, and I would have to move on to something like integration by parts. Hopefully work, or I would be moving on to some more complicated methods of trying to find the integral of this. The cosines are going to cancel out, so that's going to be 1 over 3. And I already know that the integral of e to the u is e to the u plus c. And now I can plug everything back in. And that gives me 1/3 e to the sine 3x plus c. All right. Any questions about that one? Any questions at all? Oh, where's my water? Here's my water. I need a second little side table. Cable. There we go. Maybe some Bluetooth headsets for Christmas. Let's tell Santa. All right. So, any questions about this one? Any questions at all? All right. So let's move on to the next thing. Now, this next, how many slides is this? The next 2 slides, I am going over specifically for Calculus 4, because I know that a lot of you are taking Calculus 4 at some point in the future, and I want to prep you for it. So there's a couple special rules for exponentials and logarithms that we are going to use in Calculus 4. There's no way around it. You have to. Doesn't matter if you take it with us or with WKU or with UK or Vanderbilt or U of L or wherever. Calculus 4 is Calculus 4. There's a few small little pieces that can change, but this won't. You will have to know these rules. So the first rule, and this one's very important. If you have a number out front of a logarithm, it can be moved inside as the exponential. So let's say you had 7 times ln of x. That can become ln of x to the 7th. Okay? And it doesn't have to be just an x. You could have something like 5 times ln of 2x plus 3, and that would turn into ln of 2x plus 3 to the 5th power. Okay? And something just as important, it also works in reverse. So if you had, let's say that it works in reverse. And this is very important in a lot of fields. If you have ln of x to the ninth, it can actually come out and turn into 9 times ln of x. Now think about that for a second. That means that whatever exponent you have, it doesn't have to be a number. That could be a letter up there. This could be ln of x to the r or 2r. It could be a 2r up there. It does not have to be a regular number. And I'm going to have to zoom in to get this written correctly. X to the 2r. Boom. It does not have to be a number as the exponent. That's just what I've been using. So that 2r could come out front, and now I have completely gotten rid of the exponent. Whatever that exponent is, I've removed it. I've separated it away, and now I can deal with that 2r on its own. It is now disconnected from the x, and I do not have to treat them as the same thing anymore. And so that is a very, very important rule, okay? Here's another one that is important. If the exponent contains addition or subtraction, you can split it apart into two smaller ones. So if you had something like, that you have that example right there, but what if you had something like 5x plus 8? You could split that apart into 5x times e to the 8th. That is very important in Calculus 4. We actually do that, especially during the first unit. So the first couple days of Calculus 4, we will use that rule. Okay, that just happens. Another one is if you have e raised to an ln, they cancel each other out. Okay, and it's not just that. That's the main one. So if you had something like e to the ln of x squared, well, that's going to become x squared. The e and the ln cancel themselves out. Okay. So that is a very handy rule as well that we will also use in the first unit of Calculus 4. Okay. So let's do an example here. So this is a problem directly from Calculus 4. So the first thing I'm going to do is move that up front, boom, and that gives me e to the ln of x cubed. Then the e and the ln cancel each other out, and I'm left with x cubed. That is something you will be expected to be able to do in Calculus 4. And if you can't, it's going to make your life way, way harder. I would almost say impossible to get through the problem. And you're going to have to get through it. Okay, so let's look at something like this. This is another one from Calculus 4. So right here, this is 5x plus c. So what I'm going to do is I'm going to split this apart. That's addition, 5x times e to the c. Then I am just going to now, let's say that e to the c is equal to k. And so e to the 5x times e to the c becomes k e to the 5x. So this right here is something we will use a lot in differential equations. Okay. So that's just using the rules we talked about on the previous page to split things apart, cancel stuff out, and make things a lot simpler. Okay. All right. And I think that finishes that up. So I'm going to stop here. We've got all 3 of these videos made. I'm going to get them started on the converting process and get those posted later today, and you guys can start hopefully working on the homework. So let me know if anybody has any questions, and I'll talk to you guys next week.